mathematics. We will be dealing today with the rigorous theory of approximations. You have seen some approximations in the previous lecture and in your class. What may have struck you at the time is they all look terribly unsystematic. We had one function for the harmonic approximation, we had a completely different function for the Morse potential, it was exponential rather than polynomial, and then we had some rational expression for the Lagrange potential. It felt as if somebody was sitting there and just inventing functions that look vaguely like they make sense. What we will do today is build a rigorous theory of that process, and I think today is also the first lecture that is firmly outside of what you've seen at school. So previously you may have come across derivatives, integrals, various related things like differentials, particularly if you've done better enough. But today we are going into things that were absolutely not covered at school. But again, this is something that you will encounter time and again, particularly in thermodynamics, in kinetics, in anything that has to do with modeling in chemistry. Polynomial approximations are all over the place, really, as I think that the second years will probably tell you if you ask. Okay, so you may have seen things like the following. So item 1, I guess, is a brief intro into the things. You may have been told by chemists at this point that things like exponential of 1 minus x are approximately equal, or rather exponential of just minus x is approximately equal to 1 minus x for small x. Or things in trigonometry, it's very, very useful, for example, in things like ballistics. All the writers folks are graduated using this rule, that sine x is approximately x, again for small values. You may have seen in thermodynamics, second year certainly did, that things like that, exponential minus delta E over T is approximately 1 minus delta A over T for large temperatures, so the high temperature limit, and so on and so forth. We do have a great number of expressions that must have variously glimpsed through your various textbooks that imply that something is approximately equal to something else if a certain parameter is big or large. And yesterday you have seen things like the Morse potential, so the energy of a chemical bond that is being stretched or squeezed. So if x is the length of the chemical bond, then this was some number d1 minus e minus a x minus x equilibrium, the equilibrium bond length, and all of that was squared. So this function was a dip, and we discussed it in the previous lecture. It looks like this. So that's the energy, and this is x. And so it starts off somewhere here, goes to 0, and then levels off. So that's approximately, and that is the x equilibrium. And A here is the measure of how narrow this well is. And we were discussing the various other approximations to the bond stretching potential, and we have seen that, for example, a quadratic function can show a pretty good approximation around x equilibrium. Of course, it breaks when we go far away from this in either that direction or that direction, but in some narrow area in here, it's okay. And we call this an approximation. And again, if we look at what that approximation actually is, this will be e a squared x minus x equilibrium squared. Notice in all of these cases there is the same leitmotif. We had something that was transcendental, so tough, and it became a polynomial. We had a sine, which was also a transcendental function. It became a polynomial of order 1. Exponential here became a linear function, so again a polynomial, and something complicated here became a polynomial of order 2. So all of these approximations share the same feature. Something really complicated becomes a polynomial of low order. And so this was observed at the beginning of the 18th century by Brooke Taylor, who was at the time the secretary of the Master Royal Society, and the topic is called, for that reason, Taylor series. Let us try and generalize what we have seen there. What we would like to have is some complicated which we might not even actually know. It could be a numerical solution to something else. We could have obtained the values, by experimental measurements, and so on. So some function, which, as it often happens in chemistry, particularly in quantum chemistry, is either hard or impossible to actually calculate. And what we would want to do is to say, okay, well, let us approximate this with a polynomial. So some a0, which will be the constant part of the polynomial, plus a1 x to the power 1 plus a2 x squared plus a3 x cubed plus 4x to the fourth, and so on. Now, this will be a polynomial which goes to 0, or goes to a0 in this case, when x is 0. Typically, we're not really interested at looking at things around 0. We are interested at looking at things around some reference point, so for example, x equilibrium. So what I'll do is I'll shift this polynomial a little bit and look at the following instead. F of x will be a0 plus a1 x minus x0 plus a2 x minus x0 squared plus a3 x minus x0 cubed, and so on. A construct like this, so with an arbitrary shift in x, is called the Taylor series. And a construct like that, so the special case, when the x0 is actually at the origin, is called McLaurin series. And if you've ever been in Edinburgh, look around the city centre, there's a McLaurin street in there after this exact McLaurin. Okay, so we would like to have the expressions for these coefficients, a0, a1, a2, a3, and so on. It's actually surprisingly easy. Let us do the following. Let us first put x equal to x0 and see what is going to happen. Well, if we do that, this will be 0, this will be 0, this will be 0, and everything else will be 0. So in fact, the only term that would survive is a0. So f of x0 is a0. And therefore, a0 is equal to f. Now, well, progress, right? We found one coefficient. What about the rest of them? Well, let us calculate the derivative of this with respect to x. So our f prime of x will be. Well, a0 is a constant, so it would vanish. This bracket would disappear because we are taking the first derivative with respect to x, and all of these brackets will be differentiated. So we will have a1 plus a2 times 2, because there was a square, to a2 x minus x0. The derivative of this is 3a3 x squared, and so on. So we computed the derivative. Here we differentiated the function, and here we differentiated this small, potentially infinite polynomial expression. Alright, in this derivative, let us now put x exactly equal to x naught. The result will be that this will vanish, and in fact everything else will vanish. And the only term that will survive will be a1. So, f prime computed at the point x naught is a1. And therefore, a1 is f prime of x naught. Okay, well, we found the next coefficient. Not bad. So, this is the a0, this is the a1. What about the a2? Well, let me do the next version of this. So, f double prime. a1 is a constant, it will vanish, this bracket will disappear, this bracket will get differentiated. So, f double prime of x will be 2a2 plus 3 times 2 times a3 x minus x naught plus so on. Okay, next step in the same procedure. We will put x exactly equal to x naught. This and all subsequent terms will go away. F double prime of x naught is 2a2, and therefore a2 is f double prime of x naught over 2. That's the next one. We can repeat this procedure indefinitely. We can continue differentiating both sides. We will have third, fourth, fifth, sixth, and so on derivatives of our function here. And we will have the derivatives of an infinite polynomial expansion on that side. And we will obtain a0, a1, a2, a3, a4, and so on. Let's take a good look at what is happening in here. So what is an? Every time we are differentiating, we get a higher and higher derivative of f. And a0 was the zeroth derivative, a1 is the first derivative, a2 is the second derivative. So clearly this will be the nth derivative of f, computed at the point x0. And then let's see what it's divided by. This was divided by 1, this was divided by 1, this was divided by 2. The next coefficient, the a3, will be divided by 3 times 2. The a4 will be 4 times 3 times 2. So all of that is 1 times 2 times 3 times 4 times n. So imagine we are differentiating, say, the nth power in this expansion. First the n will pop out, then n minus 1, then n minus 2, n minus 3 as you're differentiating again. And so this will be that. Such a product has a name. It's called a factorial, and exclamation mark is 1 times 2 times 3 times 4 times so on n. So it's not to be pronounced it is to be pronounced factorial in a, level books. So that's actually f n's derivative of x0 divided by n factorial. Well, guess what? We just discovered the expression for the entire Taylor series because that's the only thing we really wanted in that big expression there. So we will triumphantly write it. It took Taylor the entire book to rewrite this, and you can appreciate the power of modern calculus that, in 2018 we can do it in 10 minutes. So our f of x, I will write this expression as a sum. So it will be a sum n equals 0, so we start from a0 and all the way to infinity of an x minus x naught to the power n. So this is just a shorthand expression for that infinite series in there. And now that we know the expression for the n, we can put it in. We can see that sum. And from 0 to infinity, f n's derivative at x naught over n factorial x minus x naught to the power n. This is Taylor's result, the one that he got famous for. On the left-hand side here, we have potentially a really nasty function. On the right-hand side here, we do have an infinite polynomial, and they happen to be equal. Now, of course, not even a computer can, in practice, calculate an infinite sum. It is, after all, infinite. But thankfully, what happens is the further you go, the higher powers in this polynomial you calculate, the more accurate this polynomial becomes as an approximation to that value. So let's say if we truncate it, not at infinity, but at, for example, n equals 10, the resulting 10th order polynomial, as you will see in your classes, and if you run Mathematica, for example, it can calculate this series automatically. It will come really close to your function. It will shape and mold itself in a way that really mimics the behavior of your function around your x0. The further you go away from x0, the worse it will get, much like it happened in here. So this is actually a Taylor series with just two terms. And as you can see, around our reference point, it pushes itself really close to the function it is approximating. But as we go further left or further right, the approximation quality degrades. This is often the need in chemistry where we are not really interested in the value of a particular parameter for every possible temperature, right? Who cares what happens outside the room temperature if the process is supposed to be running at room temperature, right? If you're dealing with a human, for example, some pH control in bloodstream, if the temperature of the system is 10 degrees Celsius, the human's dead anyway. You no longer care. And so it is reasonable to expand whatever functions you have, if they're complicated, around 37 degrees Celsius, plus or minus a couple of degrees, because realistically this is what you're doing. And this is how these things are used. Okay, let me give you a couple of examples of how to calculate Taylor series, and let us start with a recipe. You can more or less glean the recipe from the way that I derived the Taylor series for you, but basically the procedure is as follows. So, recipe. Item number 1, calculate a few derivatives of your function. So, compute a few derivatives. Typically, I'd say 4 or 5, maybe 3 if you are lucky, so say up to about f 4 times of x or thereabouts. You can all differentiate by now, shouldn't be too much of a hassle. Item number 2. And this is optional. Try finding a pattern for nth derivative. Try for nth derivative. The reason this is optional is that it's not very often that we actually require the complete infinite series in practice. You'd normally want 3 or 4 terms, but if you are fishing for a complete infinite series for whatever reason, you would need to find the general expression for the nth derivative. In some cases it is easy, in other cases it is hard, but this is a creative there is no general recipe for. You have to just hypnotize it until you see a pattern. So item number 3 then, calculate all of these derivatives at your reference point x naught. Calculate derivatives at x naught. Basically substitute the x naught. Whatever it is, 0, 1, pi, doesn't matter, but put it in and calculate the value of the derivative. And then or use that expression there. So you will have all of these derivatives computed. You will have numerical values for them. Factorial is a factorial, just put the derivatives in here, put the factorials in there, and this is your x minus x naught, that's your polynomial. So you will know the coefficients, that's your polynomial, that's it, you're done. So item number 4, assemble the series. Okay, let's go through this flow chart in practice for the very famous case of the exponential function. Now, exponentials happen to be solutions for Schrödinger's equation. And so, in my daily life as a computational chemist, I am doing exponentials most of the time. In fact, I'd imagine if you ask which mathematical operations Iridi's supercomputer is doing 20 to 30% of its time, those are matrix exponentials, and my students are responsible for them. So a singularly important operation, and this Taylor series that I'm about to derive is actually how we are computing it in 2018. So even though the technique goes back to early 18th century, it is actually still used in particle chemical calculations. So f of x is e to the x. The reference point is 0. Now let us follow the procedure. Compute a few derivatives. All right. F of x is e to the x. That's the zeros derivative. F prime of x is the same, e to the x. First derivative. F double prime of x, e to the x. Second derivative. F triple prime of x, e to the x. Third derivative. And so on. Probably the luckiest case in mathematics because it doesn't really change. As you can imagine, there could be plenty of functions that by the time you have taken the third derivative, you've got the expression half the size of your A4. But not in this case. Okay, so we did it. Fine. So item number 2, try finding a pattern. All the patterns are pretty trivial, it doesn't change at all. Calculate the derivatives at x naught. So our f at x naught is exponential of 0, 1. F prime of x naught, 1. F double prime of x naught, 1. And so on. And of course, in here, f nth derivative of x will be e to the x. And then here, f nth derivative at x naught will be 1. All right, well, we do actually know all of these coefficients we need to assemble the Taylor series. So item number 4 is to build it. E to the x is equal to a sum from n0 to infinity, as per the definition here. As we just discovered, all of these derivatives are equal to 1. And so in the numerator, we simply have 1. The reference point is 0, so the x naught disappears, so we have 1 over n factorial x to the power n. One over n factorial x to the power n. And this is the Taylor series for the exponential. Let us now think about what is going to happen if this x is small, and let's put a minus in front of it. So, e to the x, we've got there, e to the minus x will be a sum, n 0 to infinity 1 over n factorial minus x to the power n. So I simply substituted minus x for x everywhere. And let us take the first two terms of this. Approximately equal. So if x is really, really small, the zeros term in here, 1 over 0 factorial by convention, there is a long answer as to why this should be the case, but we do not have the time to go in there. 0 factorial is equal to 1. So 1 over 1 is 1. Anything to power 0 is also 1. So the zeros term here is 1. The first term, so for n equals 1, 1 over 1 minus x to the power 1 minus x. Check this out. That's where this expression came from. If you do the same sign, you will discover the first term is x. This is actually the same exponential as this, except x has a fancy appearance. 1 minus, so that's your large temperature approximation in chemical thermodynamics. And if you go through the rather complicated process of differentiating that, you will discover that the zeros term is 0, the first term is 0, and the first non-zero term is the term with the power 2, and there's your parabola approximating the Morse potential. These are not the only examples by far. You will see them everywhere. This is one of the most obvious approximations people ever make almost anywhere in physics and chemistry, because it is so often the case that some parameter is either extremely small or extremely large. Okay, so this was cheating to an extent, because I've taken the simplest case there is in mathematics and I've done the Taylor series for you. Let us do a case that is actually less trivial than that, and is actually closer to practical reality, where, well, a considerable amount of thinking can be required sometimes to figure out what the Taylor series is, and that is the series for the log, and the reference point in this case would not be 0. So f of x is log x. Now the problem with the log, of course, the logarithm of x has a singularity at 0. If you want 0, you would have to take e to the power minus infinity, so it goes to infinity. And so we cannot actually use 0 as a reference point here, but we can use 1, right? Log 1 is a perfectly sensible number. So our x naught will be 1. And so we will be looking for a polynomial approximation to the logarithm function in the vicinity of 1. You may have seen those ancient logarithm tables. Your parents may have used them at school, or rather no, my parents may have used them at school, your grandparents may have used them at school. It's just an enormous book filled with numbers. There's an argument, there's a table of logs. This is how those tables of logs were actually calculated first in the era before digital computers. And okay, let us follow our recipe again. Compute a few derivatives. So let's start differentiating. F0's derivative of x is just log x. We don't do anything. First derivative of x, derivative of log is 1 over x. The second derivative is minus 1 over x squared. Minus 1 over x. third derivative is plus 2 1 over x cubed. And now put a plus here, just to make something obvious. Fourth derivative of x is minus 2 times 3 times 1 over x to the fourth. Fifth derivative plus 2 times 3 times 4 times 1 over x to the fifth. And so on. Let me just write the board here. Let's try and find a pattern. Well, clearly this is shaping up to be a factorial. If I continue differentiating this, this is 1 times 2 times 3 times 4, eventually times 5 times 6 and so on. So this is a factorial. And derivative of x will contain a factorial. N factorial. But look at this. Fifth derivative, but the factorial is up to 4, so it's not n factorial, it's n minus 1. Alright. The next thing we can observe here is the sign is alternating. Plus, minus, plus, minus, plus. The way to implement alternating signs, it's a power of minus 1. So, minus 1. Minus 1 to power 0 is a plus, minus 1 to power 1 is a minus, minus 1 to power 2 is a plus, clearly the opposite of what we want. So why don't we make this minus 1 to the power n plus 1. So here, n plus 1 is 2, there's your plus. N plus 1 is 3, there's your minus. N plus 1 is 4, there's your plus. N plus 1 is 5, there's your minus. So this minus 1 to the power n plus 1 guarantees us plus, minus, plus, minus, plus, minus in the right places. Because the even powers of this are positive and odd powers of this are negative. So as n increases, this will be jumping between plus and minus. Okay, the next thing in here, well, fifth power has 1 over x to the fifth. The sixth derivative will have 1 over x to the sixth. So 1 over x to the power n. Well, that's a complicated expression and is on the brink of what you're expected to be capable of. And as you can see, it requires a little bit of philosophy in that up to this point, computing one derivative after the other is an algorithmic process, right? You can teach them to do that, and they'll be doing that because there's a recipe. At the point when you are generalizing, the procedure becomes creative, as in there is no recipe to recognizing a pattern in it. You have to know enough mathematics to be able to get this and to write it down, which boils down in practice to experience, which means practice, 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 practice. There's no other way. All right, so this finishes our item 1 in there and item 2. We met this.
I don't understand the last fraction you got.
This one?
Yes, how did you?
Well, first derivative is 1 over x, second derivative is 1 over x squared, 1 over x cubed, 1 over x to the fourth, 1 over x to the fifth.
So it's just 1 over x to...
1 over x to the n.
Is it a minus or is that a dot?
Here.
And
here.
Is that a minus?
It's a dot.
It's a dot.
Dot.
So it's times.
So it is times because it's times everywhere. Okay, so let us now compute these derivatives at our reference point as per item number 3 in our recipe. Well, it actually simplifies things a lot because logarithm at 1 is 0 and all the 1 overs at 1 are just 1, and so the derivatives are actually quite simple. So now at 1 is 0 because log 1 is 0. First derivative at 1 is plus 1. Second derivative at 1 is minus 1. Third derivative at 1 plus 2. Fourth derivative at 1 is minus 2 times 3. Fifth derivative at 1 is plus 2 times 3 times 4. And then finally, if we put 1 into there, f nth derivative at 1 will be minus 1 to the power n plus 1 and minus 1 factorial. Right? 1 over 1 to any power is just 1. Okay, we have found the general expression for z derivative. We can now proceed to item number 4, that is to assembling the series. As per the definition, our f of x is a sum, and from 0 to infinity, f nth derivative at x naught over n factorial x minus x naught to the power n. That's the definition we've derived. Let's now have a good think. Well, our zeros derivative in here doesn't exist. So the first term in this sum is actually going to be 0. So the sum really begins from n equals 1. So it will be a sum from n equals 1 to infinity. The next thing we need to put is nth derivative in there, and we have it. It's right there. So minus 1 to the power n minus 1 factorial. So this is the derivative that we have so painstakingly obtained. N factorial is the denominator, there, and then x minus the reference point, x naught is 1, x minus 1 to the power n. Well, that looks sufficiently horrible, and this would in fact be accepted as the final answer, except there is one further simplification here that we can make. Notice what we have in the numerator in there, the factorial. It's 1 times 2 times 3 times 4 all the way to n minus 1. Yeah? In the denominator, however, we do have 1 times 2 times 3 times 4 all the way to n minus 1 and then n. That's n minus 1 factorial, that's n factorial. It is quite clear that most of that stuff will cancel, and you only are left with n in the denominator. Question?
For the sum part, would it be minus 1 instead of n plus 1?
Can you speak up?
For the sum part, is it not n max? Is it not n
Oh, yes.
plus the higher?
Well spotted, yeah, n plus 1. Yeah. That's because we had it in here. Just lost the plus 1. Alright, so most of the 2 factorials cancel each other, and so we're just left with n in the denominator. And so let me introduce you to the Taylor series for the log. Minus 1 to the power n plus 1 over n x minus 1 to the power n, and that is the final answer for the logarithm. Let us now take a good look at it. I have plotted in your handout this Taylor series truncated to a certain number of terms. So I plotted the actual log as a function of x, and then next to it I have plotted the various approximations. So that is our f of x. If you remember how a log looks, it is something like this. It goes to minus infinity, then it crosses 0 at 1, and then it grows rather slowly as the function, as the argument increases, and so this is 1. And that also happens to be our reference point. Imagine now that we truncate this series at the first term. What is going to happen in here? So if we only keep n equals 1, is actually quite simple. Minus 1 to the power 2 is plus. Denominator is 1. And then it's x minus 1 to the power 1. So it will be y equals x minus 1. And so it's the function that goes diagonally with an intercept of minus 1, and it's actually this. It's a tangent line to our log at exactly 1, and this intercept here is minus 1. And as you can see around our reference point, it's a plausibly good approximation. And so long as you're remaining in a tiny vicinity of it, that's probably good enough. If we go to the next term, if we go to the quadratic term in here, what we will have is something negative, because this will be minus 1 to the power 3, divided by 2, and then a quadratic function in here. If we actually plot that, what we will see is something like that. It's plotted in your handout. It will be a curve that gets rather close to the logarithm, and then does its quadratic business. You have an inverted parabola that has been carefully fitted and squished to be an excellent approximation in a slightly broader range. You can see that the accuracy starts deteriorating somewhere here, and perhaps up to about here you are actually okay. Whereas for our yellow line, the range of a reasonable approximation was significantly narrower. So the more terms you take in the Taylor series, the more accurate it becomes. Okay, if we go to the cubic term, what will happen is this thing will become even closer. So the cubic function will be something like this. So it will deviate from the log somewhere here, and then keep going for rather a long time until it will suddenly blow up and become a cubic function again. So for the cubic, the range of reasonable approximation is approximately up to here. So you see, the further we go, so that was linear, so n equals 1. This was quadratic, n equals 2. This was cubic, n equals 3. The further we go down the number of terms in the Taylor series, the better the approximation becomes. However, sooner or later, if we go too far left or too far right, it's still a polynomial, right? It's not a logarithmic function. And so eventually it will start either growing as a cubic or a quadratic, or decaying as a cubic as a quadratic. It will deviate from the function it is trying to approximate. So Taylor approximations are local. You can make them as good as you like. If you go to 20 terms, it will be really good, as it will start deviating somewhere here. However, well, you have to be always aware that they are approximations. The next interesting thing in here is to see what happens around this point here. It's not really an excellent scale in here, but this point is approximately 2, as we will discover on Thursday. Notice that abruptly, around 2, the approximation quality deteriorates. And it turns out, in this particular case, that no matter how far you go, even if you go to term number 100, then at this point, the approximation quality will abruptly degrade, and this point is called divergence point. And that's the subject of the next lecture. So let me give you the summary of what we've done today and wrap it up. So everywhere in physical chemistry, in kinetics, in most of physics, there is an abundance of quantities which are either very large, in which case they're reciprocally small, or they are very small naturally. Temperatures, pressures, volumes, quantities, perturbations, forces, you name it. Stuff can be small. And you have seen already, second years have seen it, I've seen it every day. The first years might have glimpsed it already, that there's plenty of relations like this, where you say, oh, okay, this is approximately some kind of polynomial. Usually a linear function, sometimes a quadratic function, but this is something that, if you open up this and read through, you will encounter this at least 30 times in various ways. Turns out that the formal framework for such approximations goes back to the early 18th century, and it's called Taylor series. And it's actually reasonably easy. As in we say, okay, let's make it a polynomial. And as soon as you make it a polynomial, then you discover that by sequential differentiation, you can actually discover all the coefficients of that polynomial. And the process is long, and I might say unpleasant, but there's nothing supernatural in it. You can all differentiate like crazy by now. I've been torturing you on and on and on and on with differentiation. This is partially why. So you are totally comfortable, all of you, with differentiating a function as many times as it takes to do. Turns out there's a recipe, essentially based on the derivation there. You compute enough derivatives to see a pattern, or enough derivatives to match what you're told. I think you are told to compute something like 6 derivatives of a simple function in your workshop problems. So item 2 is entirely optional, so looking for these complicated patterns in there, I'm certainly not going to examine. And it's not very often that you even need to differentiate it 3 or 4 times. That's about enough. Okay, you get all of those derivatives, you calculate their values at your reference points, just simply substitute them, and you get your derivatives, at which point the definition of the Taylor series kicks in. You write down the sum. In here you put the derivatives that you've calculated. This is just a factorial. That's your x minus the reference point, and you're done. And there are simple cases in mathematics like the exponential, and there are complicated cases like the logarithm, and there are truly horrible cases that I will not bother you with. The important thing is the more terms you take in the resulting Taylor series, the better approximation it becomes. However, there are mysterious points on that approximation called divergent points, which will be the subject of the next lecture. Any questions?